Hello, class. Welcome to the next Eureka math lesson. We are beginning Module 5 today. We are in Module 4 for quite a while, but now we're ready to start Module 5. Module 5, Lesson 1. In Module 5, it's shorter than Module 4, thankfully. I think there's about 11 lessons. And we're talking about functions, which are kind of connected to linear equations, kind of not. We'll talk about that later in today's lesson. But today's lesson's title is Concept of a Function, because we're all about functions for this module. Let's talk about the concept of a function. And you'll need pages 1 through 11 in your Module 5 workbooks, so get those out. Get out your note pages. And remember, as always, you are in control of the speed of this lesson, so if you need to pause or go back to catch up on your notes or to see how I did something again, feel free to do that at any time. But let's start with vocabulary. Today we have 2 vocabulary words, and the first one, of course, is going to be function, because we are all about functions for the next few weeks. A function is a mathematical relationship where every input has only one output. Every input has one output. That means every x makes exactly one y. A function is an equation, but it's not a linear equation necessarily. A linear equation, remember, occurs in a straight line. When you graph a linear equation, you make a straight line. Functions, if you graph a function, the line can be curved. So that's really the big difference. A linear equation is a type of function, but every function is not linear. But the real way to test a function, every input has only one output. Only one output. And we'll talk about that in more detail in later lessons, but that's the definition you need for today's lesson. The next vocabulary word is prediction. A prediction is telling what is going to happen based on evidence. A telling of what is going to happen based on evidence. So using evidence to tell what is happening next or what already happened is a prediction. So you're going to make predictions today about functions. Today's is kind of long because in this I kind of explained the difference between linear equations and functions. Today, Module 4 was about linear equations. That's what Module 4 was all about. But not all relationships are linear. Rates can change. Remember in Module 4, we talked a lot about slope and how in linear equations, the slope was constant. The slope stayed the same for the whole equation. Well, rates can change. When the slope of a line changes, it makes a curved line. So when the slope is constant, the line is straight. When you have a changing slope throughout the course of a line, when the slope is different in different parts of a line, it's curved and it's not linear. That is where a function can describe the change. So a function works for linear or nonlinear equations. Functions work for linear or nonlinear. So a function describes the change for when the slope is not constant. So a linear equation can be a function, but there's lots of functions that are not linear equations. A linear equation is one type of function, but there are many more functions. So we will see different types of functions in this module. Today you're going to see a function that is examples of functions that are not linear. So just so that you're aware, a linear equation is a function, but functions are not always linear. So that's what we're doing today. We're just showing you how functions are not linear. You do not just assume that functions are linear. One other note you'll need today is how to find average speed of an object. We are going to be talking about graphing objects' position in comparing distance and time, and so you are going to be measuring an object's speed. And we're going to be talking about average speed. Average speed is the distance divided by the time. So to find the average speed, you take distance 2, which is the end distance, minus distance 1, the starting distance. So the end distance minus the start distance, and the end time minus the start time. So that is the equation for average speed, distance divided by time. You take the end distance and time, you subtract the start distance and time, and you divide them. That'll tell you the average speed. So that's what we're doing today. Let's kind of compare what we're doing today with Module 4. So I do have a question, our example today that we're going to start with. Example 1 is actually a question from Module 4. Suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. And there we go. It's constant speed. So constant speed tells you it is a linear equation, linear relationship. And it even says right here, described by a linear equation. Write a linear equation. So write a linear equation in 2 variables to represent the situation, and then use the equation to predict and finish for the 4 times shown. Well, remember, when we are writing a linear equation in 2 variables, we take what we know and we build a proportion with what we want to know. What we know and what we want to know. So we know it goes 256 feet in 4 seconds. We want to know how many y feet in x seconds. So you'll remember to do this, we use the multiplication property equality, or something called cross multiply. We multiply both sides by both denominators. So on the left we can cancel the 4, on the right we cancel the x. So we get 256x equals 4y. Then we divide by 4. So we get 256 over 4x equals y by itself. And we can simplify this. We can simplify this because 256 divided by 4 is actually 64. So we get 64x equals y. That's our equation. Y equals 64x. So now we can use the equation to predict the distance traveled. So in 1 second, when x is 1, we do 64 times 1, so it goes 64 feet. When x is 2, that means it moves for 2 seconds. 64 times 2 is 128 feet. When the object moves for 3 seconds, we do 64 times 3, which is 192 feet. And in 4 seconds, the object moves for 4 seconds, x is 4, 64 times 4 is 256. So that's how we can predict how an object moves when it has a constant speed. When there is a constant speed. This is like Module 4. When the speed is constant, the slope is predictable, the change is predictable. We can use a linear equation to find it. This is exactly what we did at the beginning of Module 4. Now, for the rest of Module 4, what I would have asked you to do is graph these on a coordinate plane, turn them into coordinates 1, 64, 2, 128, and the rest. Graph them and connect them to make a line. But we're not really going to do that right now. I just wanted you to have this chart available so you can see how this object that moves at a constant speed, how it moves. Now, for example 2, we're going to compare this because example 2 is not the same. This time, the object, a stone, is dropped from a height of 256 feet. So the feet is the same, 256, 256. It takes 4 seconds for the stone to hit the ground. So 4 seconds and 4 seconds. So it moves, this object moves 256 feet in 4 seconds. This stone moves 256 feet in 4 seconds. But it's asking how far does the stone drop in the first 3 seconds? What about the last 3 seconds? Can we assume constant speed in this situation? In other words, does this follow a linear equation? Is the speed constant? So we know the last number, 4 seconds, it's going to hit the ground 256 feet below. So the last number is the same, but does everything else mean the same? Now you might say, yes, it moves the same speed all the time. Except that's not really how falling objects work. That's not really how falling things work. To test it, just take something that you can drop, if it's a ball or just a pencil, and drop it on the ground and watch it super carefully. If you watch the falling things carefully, or find a video, find a YouTube video of things falling, you will see when you're watching that when something starts to fall, it's moving slower than it is at the end of the fall. You can even think this if you push something down a hill, like if a car or a wagon is rolling down a hill. When something starts to roll down a hill, like if you take a soccer ball and roll it down a hill, when it starts to roll down the hill, it starts rolling slowly. But it gets faster and faster the farther it rolls down the hill. It is rolling the fastest at the bottom of the hill. So when things fall, when things roll down, they start slow, but they get faster. That's gravity. Gravity actually makes things speed up as they fall. So when something falls, it gets faster as it falls. And so in this one, a stone that is dropped is not like a car going down the road. The speed is not constant. The speed is not constant. You can see this if you roll a ball down a hill or if you drop something off a table. The speed is just not constant. It's not going to work. It's not going to work and follow this same pattern. It's going to be faster. So the first distance is going to be smaller. And then the gaps are going to get bigger as it goes because the speed will increase. This is how gravity works. So falling objects do not have a constant speed, which means the speed is not constant, which means no linear relationship. The slope is not going to be 64. The slope is going to be more complicated than that because it's going to change. The slope is going to change as the graph moves. In fact, if you go to page 2, the table at the top shows you what's going to happen. This shows you, and we can look at this and say, this is the table on exercise 1 through 6, page 2, is the table just like the table on page 1. So at 1 second here, the stone only falls 16 feet. So at 1 second, it's 16. At 2 seconds, it's 64. At 3 seconds, it's 144. And at 4 seconds, it's 256. So you can see the difference between a linear relationship where something always moves at the same speed. This is what happens when the speed is constant. It always moves the same. A 64 gap, a 64 gap, a 64 gap. When a variable speed, non-linear, when something speeds up. So these are the numbers for the same speed always. These are the numbers for speeding up. So for the first second, you can see it only moves 16 feet in the first second. Because it's starting to move slow, just like a ball rolling down a hill. It starts slow. So instead of moving 64 feet, it moves 16. And then after one more second, it moves another 48 feet. 16 plus 48 makes 64. So it moves 48. So this is 16 feet in 1 second, 48 feet in the second, 80 feet in the third second, so it's speeding up. So it was a 16 change, a 48 change, an 80 change, and then a 112 change. So you see the change is increasing. For this one where it was constant, the change is always 64. For this stone that's falling, because when things fall, they start slow and they get faster, the change is going up. This is always a 64 change. This change grows as time grows. So falling things are not linear. So this does not use a linear equation. You cannot use a linear equation for this, but you can use a function. A function is what we use when it's not linear. We call it a function when it's not linear. So let's explore this falling stone a little bit with our exercises starting on page 2. So they gave us this chart where they tell us where the stone is every half second. So after half a second, it moves 4 feet. After 1 second, it moves 16, and so on until 4 seconds, it hits the ground, 256 feet. So let's use this table for our exercises. Starting with name 2 predictions that you can make from this table. Well, that just means looking at the evidence and telling us what the evidence shows. So I'm just going to make 2 predictions right here. My first prediction is after 2 seconds, the stone falls 64 feet. And that is this line on my chart. After 2 seconds, the stone falls 64 feet. That's a prediction. Next prediction, let's just use this one right here. After 3.5 seconds, the stone falls 196 feet. So that is really just my predictions. I'm using the table telling me what the evidence says is going to happen. So this is the evidence. These are my predictions. Number 2, name a prediction that would require more information. Well, that just means evidence that's not on the table. So I could say, how many feet the stone falls in, let's say, 1.75 seconds. That needs more information because 1.75 seconds is not on the chart. So I need more information because this X is not on the chart. So that's just what the predictions are asking you to do. Look at the chart, look at your evidence, and see what you think will happen if we drop the stone. So my prediction that I can make, I can make a reasonable guess after 2 seconds, after 3.5. But if I want to make a prediction about 1.75, I'm going to need more information. So that's just practicing using predictions according to functions, predictions with functions. Let's look at number 3. What is the average speed? And here we go, average speed. That's why I gave it to you in your notes. So you need the equation. They give you the equation right here too. So that's 2 times you've seen the average speed equation. What is the average speed of the object between 0 and 3 seconds? How does this compare to the average speed calculated over the same interval in example 1? So between 0 and 3 seconds for our falling stone. So remember, average speed is distance divided by time, d2 minus d1 divided by t2 minus t1. So for this, the stone, the t2 is 3 seconds, and the t1 is 0 seconds. So between 3 seconds and 0 seconds. So now I need to use my chart to see what the distances were for 3 seconds and 0 seconds. So for 3 seconds, the distance was 144. So d2 is 144 and t2 is 3, because 144 feet in 3 seconds. For 0 seconds, well, in 0 seconds, the stone moved 0. So the average speed is the distance where we stopped measuring minus the distance where we started, and the time where we stopped minus the time where we started, which is just 144 divided by 3. So the average speed for the stone in those 3 seconds is 144 divided by 3, which is 48. 48 feet per second. 48 feet per second. So for the first 3 seconds, the falling stone moves at 48 feet per second. In example 1, how fast was this object moving? Well, this object was moving, remember the slope was 64. So in example 1, it was moving at 64 feet per second. So 64 feet every second means it's moving at 64 feet per second. That's the slope. So how does that compare? Well, if you look, the first example for the first 3 seconds, so the object speed in first 3 seconds is actually greater than the stone speed in the first 3 seconds. So that's how it compares. The object from example 1 is moving faster in the first 3 than the stone is moving in the first 3, because the stone only moves 48 feet per second. The object is moving 64. Good. We're just doing every question one at a time just to see what's happening. Let's look at exercise 4. Let's take a closer look at the data for the falling stone by answering the questions below. How many feet did the stone drop between 0 and 1 second? So what is the feet difference between 0 and 1? So between 0 and 1, how did it move? This is part A. For part B, between 1 and 2. So between 1 and 2, this is part B. Between 2 and 3, how many feet did it move in between 2 seconds and 3 seconds? That's part C. And for part D, how many feet did it drop between 3 and 4 seconds? So between 3 and 4 seconds, part D. So what was the feet change? How much did it change? Well, for part A, what was the change? Well, at 1 second, we're at 16, and we start at 0. So that's a 16-foot change. For part B, what about second number 2? So at 2 seconds, we stop at 64, we start at 16. So we do 64 minus 16. That's a 48-foot change. For the third second, second 3 ends at 144. Second 2 ended at 64. So 144 minus 64, that's an 80-foot change. What about for the last second? Well, we finish at second 4 at 256. We started second 4 at the end of second 3, 144. So 256 minus 144, we have a 112-foot change. So in the first second, it moved 16 feet. Second 2, it moved 48 feet. Second 3, it moved 80 feet. Second 4, it moved 112 feet. So you can see every second it falls, it moves more. So let's put these answers on exercise 4. How many feet did the stone drop in the first second? 16 feet. How many feet did the stone drop between 1 and 2 seconds? 48 feet. How many feet did the stone drop between 2 and 3 seconds? It dropped 80 feet. And part D, how many feet did the stone drop between 3 and 4 seconds? It dropped 112 feet. And then what do we notice? Compare these. Compare the distances the stone drops from one interval to the next. What do we notice about the dropping stone? Well, I notice that we have 16, 48, 80, and 12. The drop distances, what I notice, are increasing with time. The drop distances are increasing with time, which means they're getting it's dropping more as the time goes on. That's what I noticed. So in other words, the stone is speeding up. The stone is speeding up. The stone is getting faster. Remember back in our example 1, this object stayed the same speed the whole time. But the stone from example 2 in these exercises is speeding up, which means it's not a constant slope, which means it is not linear. This is a function, but it is not linear. Let's look at exercise 5. What is the average speed of the stone in each interval half second? For example, the interval from 3.5 seconds to 4 seconds. So they want us to find the average speed for every half second. So we need to do every half second. So let's do this. So we have between 0 and 5 seconds. So we need to do, remember the average speed, we take 0.5 minus 0 for this one, and we have to find that those are the times, 0.5 and 0. This is T2, this is T1. Now we need to find the matching distances. Well, remember 0.5, the distance was 4 on our chart, which means we have 4. And for 0 seconds, the distance was 0. So we have 4 divided by 0.5, which is 8 feet per second in the first half second. What about between 1 and 2? So we do T2 is 1, T1 is half, so we do 1 minus 0.5. And we need to do the matching times. So at 1, it was 16, and at half second, it was 4. So we do 16 minus 4, because D2 minus D1. So that gives us 12, and 1 minus 0.5 is 0.5, which means for that half second, it was moving 24 feet per second. So the speed in this half second was 8 feet per second. Half a second later, it's moving 24 feet per second. That's a big increase in speed. Let's check the next one. Next one, again, we have between 1 and 1.5. So the later one is T2, then we have T1. So we do 1.5 minus 1, and we find the matching distances for 1.5 and 1, which is 36 and 16. So D2 is 36, D1 is 16. So we do 36 minus 16. That gives us 20. And 1.5 minus 1 is a half. 20 divided by 0.5 means it's moving at 40 feet per second. So the speed is increasing. We start at 8. Then half a second later, it's moving at 24 feet per second. Then half a second later, it's moving at 40 feet per second. What about the interval between 1.5 and 2? So this time we're doing between 2 and 1.5. So find the matching ones. We have 64 and 36. So we do 64 minus 36. This is just using our chart. 64 minus 36 is 28. 2 minus 1.5 is 0.5. So here, 28 divided by 0.5, it's moving at 56 feet per second. Now I'm doing this in my head. You might need a calculator for these divisions. That's okay. But the speed is still increasing. I think exercise 5 continues to the next page. So what's the interval between 2 and 2.5? So still we're doing this time we're doing 2.5, the difference between 2.5 and 2. So 2.5 is 100, 2 is 64. So we do 100 minus 64. That gives us 36. 2.5 minus 2 is 0.5, which means for this half second, it's moving at 72 feet per second. The speed is increasing. What about 2.5 and 3? Well, we're doing 3 minus 2.5. Find the matching ones. 3 is 144. 2.5 is 100. So we do 144 minus 100. That gives us 44 divided by 0.5, which means it's moving at 88 feet per second. Which, remember, for the first half second, it was moving 8 feet per second. When it started, that's how fast it was going. Now it's going this fast. That's 11 times faster after 2.5 seconds. What's the interval between 3 and 3.5? Well, now we're going to do the time on the denominator and the matching distances in the numerator. So we need 3.5 is 196, 3 is 144. So 196 minus 144, that is 52. And 3.5 minus 3 is 0.5. Which means now it's going 104 feet per second. You can see by calculating average speed that it's speeding up. We saw when we looked at the distances, we said it's speeding up. Now we have the speeds that are getting bigger every half second. Speeds are increasing. What is the average? Compare the average speed between each time interval. The average speed is increasing. Average speed is increasing. The average speed is increasing. And if you look, you can even figure out how much it's increasing. Because if you look 8 to 24 to 40 to 56 to 72 to 88 to 104, if you do the math, 8 plus 16 makes 24, plus 16 makes 40, plus 16 makes 56, plus 16 makes 72, plus 16 makes 88, plus 16 makes 104. Average speed is increasing by 16 feet per second every 0.5 seconds. So it's going 16 every, it is increasing by 16 feet per second. So it's getting faster by 16 feet per second. So the speed is changing, but the gap of speed is not. And this is gravity right here. This is how fast gravity works. 16 feet per second every half second turns into 32 feet per second every 1 second, and that's gravity. So this, why is the speed increasing? Because gravity is pulling it. But yes, the speed is increasing. So the changing speed is not linear. The speed is linear because it's always changing by 16, but the position is not linear. So this is just evidence of how functions work. Number 6, is there any pattern to the data of the falling stone? Record your thoughts below. There is a pattern, but it is kind of related to what I just saw. The pattern is that the speed is increasing by 16 feet per second. So you can talk about that. There is a pattern. You can see any pattern you want to see. You can try to make a pattern right now if you like, but really it's not a linear pattern is the thing. You're not going to find a linear pattern. You're going to find the pattern is 16s. The pattern is 16s because right here, this is 16 times 1. This is 16 times 4. This is 16 times 9. And this is 16 times 16. So just like we said, it is 16 right here. The pattern is really 16s. The pattern is really 16s. Which what you see here is, so to see the pattern, what you're going to see is like 1 squared makes the 1. 2 squared equals 4, and that's where the 4 comes from. 3 squared makes the 9. 4 squared makes the 16. So that's the pattern. What you're doing is really the y equals the 16, which is the key to the pattern, times the t squared. That's the pattern that you might see. That's the pattern you might see. It's the 16 that we found from exercise 5. 16 is the increase, times not just the t, but the t squared. Because it's 1 squared makes the 1, 2 squared makes the 4, 3 squared makes the 9, 4 squared makes the 16. So yes, there is a pattern, but it's not linear. You know this is not linear because in Module 4, you learned that the exponent has to be 0 or 1. This is an exponent with a 2, so it's non-linear. So yes, is there a pattern? Yes, but it's non-linear. It is a function, but it is non-linear. So this is just, we're expanding your mind right now. In Module 4, we talked about linear relationships. Now we're talking about functions, which can be relationships that are not linear. So this is a lot like Module 4, just now we're talking about things that are not linear, not in straight lines. So now you're going to practice more of this. That's our practice work. Remember how to find average speed and all that good stuff. For your individual work, the lesson summary is on page 5. I'm just really giving you the definition of a function again. Page 7 is the exit ticket. Let's slide that to the back. You have a homework helper on page 9 and 10 you can use to help you with this. Page 11 is your problem set. Your problem set is all about a ball being thrown in the air. And so this is where the ball starts over here at point A and it hits the ground at point B. So the ball is thrown, it hits the ground over here. This is the path the ball follows because the ball goes up and it comes down. X-axis right here is the distance the ball moves. The y-axis shows you the height of the ball. So this is how far the ball moves horizontally. This is the height vertically. And then you're going to go through A, B, C, D, E, and F, and they're going to ask you to label parts of this graph. They're going to ask you to find average speeds. They're going to ask you to do all that kind of label coordinates, write coordinates, and they're going to ask you to make predictions. Remember, my answers to the problem set are online. So if you get stuck, you can always look at my answers, and my answers will help you. Also, if you need more help, you can always reach out to me, and I will help you with whatever you need for this. I'll talk you through the problem set if my work on the Google Classroom is not good enough. But when you are confident and you got all your questions answered, you are ready for the exit ticket, which was back on page 7. This exit ticket is about a ball bouncing across the schoolyard. So it falls down, it bounces up, it falls down, it bounces up, and it shows you this bounce on the graph. And everything is labeled for you. You have the coordinates. It says find the heights of the ball at these things. You're going to find how high the ball is at these times. And then for part B, what is the average speed of the ball for the first 0.25 seconds and the average speed for the next 2.25 seconds. So you're going to practice reading the graph to tell me the heights. You're going to use the heights to find the average speed. And then you're going to answer, is the height of the ball changing at a constant rate? So is the height changing at a constant rate? Or is it speeding up and slowing down? Hopefully you can see from the shape of the graph the answer to part C, because this is not linear. So that should tell you the answer to part C already. But do your best on the exit ticket. Remember, ask me for help. Take a picture of your exit ticket, turn it into the Google Classroom so that I can see you understand this concept, and get ready for lesson 2 tomorrow. Thank you for paying attention. Good luck. Have fun. Work hard. Persevere.